Okay, so let's talk about the history of DES. Essentially, in the early 1970s, IBM realized that their customers are demanding some form of encryption. And so they formed a crypto group, and the head of that group was Horst Feistel, who in the early 70s designed a cipher called Lucifer. Now it's interesting, in fact Lucifer had a number of variations, but one of the later variations in fact had a key length that was 128 bits and a block length that's also 128 bits. Okay? In 1973, the government realized that it's buying many commercial off-the-shelf computers, and so it wanted its suppliers to actually have a good crypto algorithm that they could use in products sold to the government. So in 1973, the National Bureau of Standards, as it was called at the time, put out a request for proposals for a block cipher that's going to become a federal standard. And in fact, IBM submitted a variant of Lucifer. That variant actually went through some modification during the standardization process. And then finally, in 1976, the National Bureau of Standards adopted DES as a federal standard. And in fact, for DES, it's interesting that the key length was far reduced from Lucifer. It's only 56 bits, and the block length was also reduced to 64 bits. And in fact, these decisions, especially the decision to reduce the key length, is kind of the Achilles heel of DES and was a source of many complaints over its life. In particular, already back in 1997, DES was broken by exhaustive search, meaning that a machine was able to search through all 2 to the 56 possible keys to recover a particular challenge key. And in fact, we're going to talk about exhaustive search quite a bit. It's quite an interesting question, and there are various ways to defend against exhaustive search. And basically, this 1997 experiment kind of spelled the doom of DES. It meant that DES itself is no longer secure, and as a result, the National Institute of Standards, as it became known, issued a request for proposals for a next generation block cipher standard, and in 2000 it standardized on a cipher called Rheindahl, which became the Advanced Encryption Standard, AES, and we'll talk about AES later on. But in this segment I want to describe how DES works. Now DES as a cipher, it's an amazingly successful cipher. It's been used in banking industry. In fact, there's a classic network called the Electronic Clearinghouse, which banks use to clear checks with one another, and DES is used for integrity in those transactions. It's also used in commerce. In fact, it was very popular up until recently as the main encryption mechanism for the web. Of course, now that's been replaced with AES and other ciphers. Overall, it's a very successful cipher in terms of deployment. DES also has a very rich history of attacks, which we'll talk about in the next segment. So this is what's known as the DES challenge. So let me explain how the DES challenge worked. The challenge was issued by a company called RSA. And what they did is basically they published a number of ciphertexts, but 3 of the ciphertexts had known plaintexts. So in particular, what they did is they took the message here, the unknown message is : and you can see they broke it up into blocks. If you look at these are basically 8-byte blocks. 8 bytes, as you know, is 64 bits. Right? So each one of these is 64 bits. And then they encrypted them using a secret key. They encrypted all using the same secret key to get kind of 3 ciphertexts. So this gives us 3 plaintext ciphertext pairs. And then they gave us a whole bunch of other ciphertexts, C4, C5, C6. And the challenge was decrypt these guys using the key that you found from an exhaustive search over the first 3 pairs that you were given. Okay. So that was called the DES challenge. And let me tell you a little bit about how long it took to solve it. So interestingly, in 1997, using an internet search, using distributed.net basically, they were able to search through enough of the key space to find the correct key in about 3 months. You realize the key space has size 2 to the 56, but on average you only have to search through half the key space to find the key, and so it took them 3 months. Then kind of a miraculous thing happened. The EFF actually contracted Paul Kocher to build special purpose hardware to break DES. This was a machine called DeepCrack. It cost about $250,000, and it broke the next DES challenge in only 3 days. Interestingly, by the way, RSA said that they would pay $10,000 for each solution of the challenge, so you can see that this is not quite economical. They spent $250K, they got $10,000 for solving the challenge. The next thing that happened is in 1999, RSA issued another challenge, and they said, well, you got to solve it in half the time of the previous solution. And so using both DeepCrack and the internet search together, they were able to break DES in 22 hours. So the bottom line here is essentially DES is completely dead. Essentially, if you forget or you lose your DES 56-bit key, don't worry. Within 22 hours, you can actually recover it. And in fact, anyone can recover it. And so DES essentially is dead and no longer secure. And just kind of a final nail in the coffin, as hardware technology improved, there was another project called Copacabana. They used FPGAs, just off-the-shelf FPGAs, only 120 FPGAs. It only cost $10,000, and they were able to do an exhaustive key search in about 7 days. So very, very cheap hardware, just off the shelf. You can break DES already very quickly. So the lesson from all this is essentially 56-bit ciphers are totally, totally dead. Now let's move on to the last type of attack that I want to mention, which I'll call quantum attacks, which are, again, these are generic attacks on all block ciphers. So let me explain what I mean by this. So first of all, let's look at a generic problem. It's a generic search problem. Suppose I have a function on some large domain X that happens to output either 0 or 1. And it so happens that this function is mostly 0, and there's like maybe one input where the function happens to evaluate to 1. And your goal is basically, find me the input where the function happens to be 1. Maybe there's only one such input, but your goal is to find it. Well, so on a classical computer, what can you do? The function is given to you. It's given to you as a black box. So the best you can do is just try all possible inputs. So this is going to take time, which is linear in the size of the domain. Now, it turns out there's an absolutely magical result that says that if you build a computer that's based on quantum physics as opposed to classical physics, you can solve this problem faster. So let me explain what I mean by this. So first of all, in the 70s and 80s, it was observed, I think it was actually Richard Feynman who observed this initially, that said that it turns out to be very difficult to simulate quantum experiments on a classical computer. So Feynman said, hey, if that's the case, maybe these quantum experiments are computing things that a classical computer can't compute. So they're somehow able to compute very quickly things that are very difficult to do classically. And that turned out to be correct. And in fact, the example I want to show you is one of these amazing things that, in fact, if you could build a quantum computer that's using quantum physics, then in fact you can solve this search problem not in time x, but in time square root of x. So somehow, even though the computer doesn't know anything about the function f, it's treating it as a black box, nevertheless, it's able to find a point where the function is 1 in time square root of x. I'm not going to explain this here, but at the end of the class, we're going to have an advanced topics lecture. And if you'd like me to explain how this algorithm works, I can explain it in that advanced topics lecture. It's actually quite interesting. And in fact, quantum computers have quite an impact on crypto. And again, as I said, I can explain this in the very last lecture. All right. So what does this have to do with breaking block ciphers? So far, it's just a generic search problem. Well, actually, I guess I should say before I show you the application, I should mention that, well, you might be wondering, well, can someone build a quantum computer? And this is still completely unknown. But at this point, nobody really knows if we can build large enough quantum computers to actually take advantage of this beautiful algorithm due to Grover. All right, so what does this have to do with block ciphers? Well, so suppose I give you a message and a ciphertext pair. Just one or just a few. We can define a function as follows. It's a function on k. It's a function on the key space. And the function will basically output 1 if it so happens that the encryption of M with K maps to C, and it will output 0 otherwise. Now we argue that basically this is exactly the type of function that's 1 at one point in the key space, and that's it. So by Grover's algorithm, we can actually find the secret key in times square root of K. So what does that mean? For DES, this would totally destroy DES. This would say that in time 2 to the 28, you can find a key. 2 to the 28 is about 200 million, so 200 million steps, which is, this takes a millisecond on a modern computer. This would totally destroy DES. But even AES with 128-bit keys, you would be able to find the secret key in time roughly 2 to the 64. And 2 to the 64 is these days considered insecure. That's within the realm of exhaustive search. And so basically, if somebody was able to build a quantum computer, we would then say that AES 128 is no longer secure. Instead, if somebody, if tomorrow you open up the newspaper and you read an article that says, so-and-so built a quantum computer, the consequence of all that is that you should immediately move to block ciphers that use 256 bits, because then the running time of Grover's algorithm is 2 to the 128, which is more time than we consider feasible. And basically there are example ciphers with 256 bits. For example, AES 256. This is one of the reasons why AES was designed with 256 bits in mind. But to be honest, this is not the only reason. There are other reasons why you wanted to have larger key sizes. Okay, so this is, as I said, just a taste of the different attacks on block ciphers. And I'm going to leave it at that. If we decide on quantum for the last topic of the course, then we'll cover that in the very last lecture.